Welcome, Matei.
All right, thanks a lot, Alexi. Yeah, and as Alexi said, I can see all the questions in the chat while I'm presenting, so I'll be able to see and answer them. Let me just make sure I pop that open here. Yep. So yeah, by the way, I see someone asked about the website for Reactive Foundation. I guess Alexi can send that out. Okay, so you can see the screen, right?
All good.
Okay, great. Yeah, so this is a talk I've given a few times before, but mostly at universities and at academic conferences. So it's about building, large-scale cloud software at Databricks and what we've been doing there. And I think there are some pretty interesting aspects here for maybe any software engineer that has to deal with really large-scale systems, and maybe also people working on enterprise products for other companies to consume and so on. So I hope you find it interesting. And at Databricks, all of our control plane services are written in Scala. Obviously, Apache Spark itself, which is what we use to run a lot of our workloads, is written in Scala too. And we have a bunch of lessons on that, and we actually have a few other talks we've given on the Scala specific things we've done as well. So I'll talk a little bit about how we built our software stack. So let me just start with the setup and why it's challenging to build cloud software, especially when running these large-scale workloads and some of the kind of issues we run into, and then I'll talk about how we tackled them. So by the way, this talk has contributions from our whole engineering team. Really, this is the majority of the work we do, is making sure that these applications can keep running reliably and securely. And these are 6 people who contributed, especially significantly to the work here. So these are people who run some of the software teams that manage our platform. Ali is our CEO and was also our head of engineering early on, and came up with a lot of the designs that we're still using for various things. Okay, so let's start about why cloud software to begin with, which is kind of this interesting trend in the industry. And then I'll talk about what we're doing at Databricks and some of the challenges and solutions we've run into. Also some questions for things that I think nobody really knows how to do well yet. Okay, so why the cloud? So if you look at traditional ways of delivering software to customers, the traditional way has been packaged software, where your development team creates these releases of the software, like Oracle 11 or whatever, Windows XP or whatever it is, and then each release takes some time to make. You build it, you test it, you package it up. It might take 6 to 12 months, and then you ship these to the customers, and then the customers have to install it. So they have maybe different installations of it, and each customer has to have some users, but also some operations people who manage that installation. So this also adds to the latency of getting the software deployed, because if you're a customer, you may not want to immediately set this thing up. It takes time to migrate to it, so it can also take 6 to 12 months for them to do it. Now, the difference with cloud software is that of course, the vendor takes on the ops role as well. So they develop and operate it for you. And that means you can push new versions out quite quickly. We do every 2 weeks for most things at Databricks, and other things are even faster. They can be like every few days if needed. And so they manage that for you. It's more work for the vendor, but it also means that the users have to do less stuff. In particular, you can have more users and fewer operations people and less overhead, because a lot of the work to keep it running is done by the vendor. You still need some ops, of course, to configure everything and make sure it adheres to your policies and so on. Okay. So why would people want to use cloud software? So actually, in most areas of enterprise software, this is really the most popular way to buy stuff now. And basically, if you're creating any kind of product that's not cloud software, your main competitor is usually some cloud thing, and your product had better be a lot better to beat out those self-managing features of the cloud product. So there's a few reasons. So first one is that the management is built in, which is just more valuable than just a bunch of bits. If I give you a CD with like even the very best database software in the world, your experience with that might still be kind of crappy because you don't know how to operate it super well, and you have to do a whole lot of work to do that. Whereas here, that operation, aspect of it is bundled into the product. Another important advantage is elasticity. You can pay as you go. You don't have to buy like a huge chunk of it up front and then not use it. So that's kind of nice. And then finally, it's the fast release cycle. Like just imagine I told you that you could get a product from 2 years into the future today. That could be pretty nice. And that's what happens because of this faster release cycle, essentially. But there are also some differences in building it and some significant challenges. So pretty much, the main benefit of building stuff this way is the fast release cycle and fast feedback. It's also kind of nice that you'd have to maintain fewer software versions. You don't have people who are running these legacy, 5 and 10-year-old versions that you still need to support. But one of the main challenges that you really, you don't have to worry about nearly to the same extent with packaged software is how to keep upgrading without regressions. And it's really hard to do this because you're changing stuff every few weeks and pushing it out, but it's critical for customers to really trust your cloud system. And this can include any kind of things that might change or regress, including APIs, semantics, performance regressions, all that stuff, right? When you're using managed software, like let's say Gmail, you never worry about, which version of Gmail am I on today versus yesterday. But it means that they better make sure that all the new versions keep working. And if your software is not just a consumer thing, but something with an API and something with, performance characteristics that are important to keep scaling, then, it gets even worse. The other challenges are to do with operations. So building a multi-tenant service, how do you make sure that you can have maybe thousands or maybe even millions of concurrent customers that share some infrastructure in a way that's still secure and that isolates them from each other in terms of performance? That's something you don't need to do for on-prem stuff because everyone installs their own copy. And then operating the service, monitoring, and so on. It's obviously more work that you have to do. Although you could argue that someone would have to do that anyway, even with on-prem stuff. And finally, you do get the advantage tied to the fast feedback loop of getting real-time usage data. So we use that a lot to see what's happening and catch issues early and fix them, and also to guide our product development. Okay. So about Databricks itself, so we are, cloud platform company. We were founded in 2013 by the team that originally created Apache Spark at Berkeley. And we just provide this platform on top of Amazon and Azure that you can use to set up, data and machine learning applications in your company. So that's the idea. So. And it's only in the public cloud. We have over 5,000 customers on those now, and we actually operate at really large scale. So we have millions of VMs launched per day in each of these public clouds. They're processing exabytes of data per day. We have over 100,000 users now, and the scale of our service, because all the jobs are large scale, is actually larger than many of the cloud providers built-in machine learning and big data services. So it's definitely getting up there. On Azure, we've also partnered with Amazon so that they basically sell our service as an Azure product. So, so definitely like pretty large scale. And we have about 240 engineers. So we actually launch and manage more than 10,000 VMs per engineer each day. So definitely a lot of stuff has to be automated. This is a plot that shows how kind of the scale of our platform has been growing over time. So this is showing the number of VMs we're managing each day. You can see it's going up pretty quickly. It's continuing to go up this year as well. So it might look like we weren't doing anything in 2017 and before that, but actually we were working hard, of course, to get the first few use cases at our customers. And then once someone is set up with the platform, they can naturally increase the workload on it, migrate more stuff, create new use cases and so on. So the past ones keep going, and of course, new ones keep being added. So we were really excited that we grew usage close to a factor of 3 last year, actually, in 2019. And it's already growing, it's already like almost doubled this year if you look at this plot. So, this is one of the exciting things about the elastic pay-as-you-go model is if people like the product or if the applications that they build are successful, they can very easily add more stuff on it. Of course, the problem for us is how do you deal with this fast growth where, while you're trying to build your new features and so on, something that you built might be starting to tip over or break in some way because the scale of it is going so quickly. Just to give you a sense of like what kind of companies use Databricks, this is just like a marketing slide with some of the customers. But the main thing is there are, I think everyone on this call, if they're from Silicon Valley, is probably very familiar with kind of ad tech and media companies, the kind of thing you'd see in Silicon Valley. But they're also like really serious, enterprise and kind of, government organization type use cases that are using large volumes of data and technologies like Apache Spark today. Just as examples, a lot of biotech companies are using these things to develop new medicines or to process medical records and kind of see what's happening there. There's actually like some of our customers have written, new research papers on these things. There's also really interesting use cases in finance or in security or in Internet of Things where people have these like, all these devices out there where they're trying to collect information about how these are being used. So these are just some of them. Okay, so I see a couple of questions actually. So one question is, we're assuming that customers bring their data to the cloud. What happens if they're too distributed? So yeah, and they can't even upload the data to the cloud. So there's definitely a potential issue. We've seen that, especially because cloud providers give you many geographic regions, a lot of these use cases set up, basically, if you are an enterprise and like you're setting something up, like suddenly you have smart meters for power, or you have like, factories all over the world, you're trying to put in sensors to do predictive maintenance. The public clouds are a pretty good way to get compute infrastructure in each geographic region with the same API so that you can have, somewhat local data processing. If you're not able to upload even to a cloud provider in the same region, then you have to run some stuff on the edge. And we see some people doing this. We don't cover this use case as much, but we have some examples where like we let people on Spark cluster on the edge, and then it summarizes data and uploads something. So it's not going to cover everything, but there are quite a few things where if you're trying to set up a new kind of data collection infrastructure, and especially if it's worldwide, one of the cloud providers is a pretty good bet to just quickly have an environment like in every country without having to stand up like, 30 different data centers and whatever. And there's also a question about private cloud customers. So almost none, basically, like all our revenue is on public cloud, is on Azure and AWS. In some cases, we have partnerships with, or special setups with some companies so they can also run things on premise, but these are a small fraction of revenue. And we actually we try not to do a lot of them because it's a lot of custom engineering for something that, it's going to be very unique to that organization. So, as a startup, we have to focus on certain things, and we're focusing on what will reach the most users, especially in the future, a few years from now. Where do we think that most of them will be? Okay, cool. So that's a bit of like what we do. So you can imagine, like all the work to run a data pipeline in one company, we have to do it for like maybe up to 5,000 companies that, and maybe for some of them, it's also replicated in several regions. And we basically have to automate all that. And in terms of what's involved in the product, this is just a very high level overview. So there are users, there are different interfaces to it, including like data science, notebooks, scheduled jobs, and just SQL for visualization and analytics. And these all run in our control plane. So this is some machines that we own. And then there's also what we call the data plane, which does the computation. And we've set this up right now so that you bring your own Amazon or Azure account and you give us an IAM role that lets us launch clusters in it and access some of the storage, and we run the computations in your cloud account. So it's kind of an interesting setup. The benefit of this is that if you are some large customer of AWS or Azure, maybe you've already negotiated a discount with them. Maybe you have some way of managing your VMs, like something that oversees all of them. Maybe you've got reserved instances, and you can just use all of those for your Databricks workloads because we run on your account. Of course, an alternative is for us to run all the compute. We haven't done that, but for some customers, that's also an interesting approach because maybe they don't have the expertise to manage this. So it's something that we may want to do in the future as well. And then within this, so we just install what we call Databricks Runtime to execute the clusters. And then the stuff that we actually run, we try to make all of the APIs that you use to write your applications open source so that you can easily find a lot of users who know how to do them. And you can also run them in other environments that are not Databricks, and you're also not locked into us. So again, if you go back to the value of the cloud services, a huge part of the value is the automatic management. So it actually kind of makes sense to say, look, we'll focus our engineering on these automatic management things that are really hard and that provide differentiated value. And then in terms of APIs, we'll try to work as much with the community as possible. We're not going to create like a competitor to TensorFlow or something. We'll just make it easy to run TensorFlow on this platform and benefit from all the other stuff happening in that ecosystem. So that's kind of been our approach in terms of the workloads. Okay, so that's a little bit about us, but going back to the challenges, we've got all the usual challenges of software as a service, high availability, security, and so on, plus the workloads themselves being large scale, which means that you can easily imagine, and it's happened before, that someone runs like one Spark job on our platform that talks to our control plane, and that becomes like a denial of service attack because it's a very large job that's making API calls. And we also get to see all these like weird edge cases and very rare failures that happen with cloud providers with these millions of VMs. So anything from like, network packets being corrupted by bit flips to like, very rare issues with the Linux kernel and stuff like that. We've run into quite a few of those. And so we obviously have to make it easy to catch those and hopefully recover from them automatically without even paging us or even having the customer notice that something went wrong in some of their VMs. Okay, so I'll talk in terms of more detail about four specific things that we learned. So what are the causes of errors, especially the ones that are hardest to catch? How to test for scalability and stability are very important to prevent these. Building these control planes that have to deal with potentially very bursty workloads, and then evolving big data systems for this cloud environment, making them easier to manage and sort of more serverless if possible. Yeah, I also saw a question from Sam about, are we looking at federation? We're not, if you mean across clouds and so on, we're not doing a ton there, but we do have, we try to provide APIs that make it easy to deploy the same pipeline in many places, similar to something like CloudFormation. So that helps with that aspect. Yeah. Cool, okay. All right, so I'll talk about what goes wrong in these kind of systems at this large scale. Again, like if you look at, say, academic research on this, or like read books on it or whatever, there are many kinds of failures that people worry about, and some of them are really well studied. So things like software bugs, how can you check them? Can you statically check your software? Network configuration, crash failures, these all happen, and they are well studied, and there are solutions for them. But if we look at like which issues have the largest impact, interestingly, in this kind of cloud and business to business like service setting, we see a lot of problems that aren't as carefully studied, and where it's not as clear what to do about them. So in particular, scaling and resource limits, workload isolations, and updates and regressions. And this last one especially, I think, is kind of new to the SaaS and kind of API delivery model, just because people weren't delivering software that way until pretty recently, basically until the last 5 to 10 years when it became very popular. Okay. So just to give you a sense, this is an overview from, I put this together second half of last year on some of the what caused significant outages for Databricks. By significant, I mean that this is something that took down production workloads, such as scheduled jobs or streaming jobs for multiple customers. So that's like a large outage, and there are smaller things like this button on this dialog box wasn't working or whatever, but those are usually easier to find and to fix. But these are ones where someone had to redo work essentially to handle with them. So you can see, there are quite a few different causes, but the main ones have to do with scaling. So scaling problem in our services where something changed in the workload, or maybe we put out a new version of the service that didn't scale as well as the previous one. That's 30%. Interestingly, some of them are from underlying cloud services where something there was not working. I'll give a few examples. Insufficient user isolation. This is where some user is placing high load or doing something unusual. And because these are multi-tenant services, it brings down others as well. And this can be very hard to fix because someone might have a reasonable looking, let's say, API request rate, but then their specific requests are causing lots of memory pressure, or they're causing runaway queries in the database or something crazy like that. And so you kind of want to isolate them throughout the stack. So this is, I think this is still kind of an open question, how to do this super well. And then we also had deployment misconfigurations are another one that I think is more common that people know about. So anyway, if you just look at it at a very high level, about 70% of them are only related to scale. These wouldn't happen if you only had like one user or one customer at a time. So these are actually some of the hardest things to fix. So here are just some examples of the issues we've seen. So an example of like cloud provider infrastructure is cloud networks. These virtual networks are not the same as real networks. They often have limits on, let's say, how many pairs of VMs can connect, or how many connections each VM can have to different VPCs or things like that. And when they can fail in very weird ways, where some of your packets are going through the connection and some of them are not, which is different from a physical network where, like, if the cable breaks, none of the packets are going through. So that's an interesting cause. Automated apps creating large load, very large requests, slow VM launches and shutdowns. This is another cloud provider thing where you ask it to launch a VM and then it takes 30 minutes. And if you're trying to keep state and memory and stuff like that, it can easily explode while you're waiting for these to come back. And then data corruption writing to cloud storage. So I'll just give you an example of one outage that highlights some of these, and I'll get back to some questions because I saw them after. So this is an outage where we observed that at some point, some customers, like production jobs, were aborted. The system decided to cancel their job. And why did that happen, right? That's kind of bad. The jobs were chugging along fine, and we just decided to shut them down. So just to help you understand what's going on here, we basically have this job service. It's a multi-tenant service that looks at the schedule of what we need to run, and then it launches jobs on these customer clusters. And because these are in the customer's resources, you have to go through the cloud network to talk to their virtual private cloud or whatever it is that they're running in. Okay. So what happened is that one customer was submitting lots of jobs per second on the same cluster. Interestingly, this customer had set up basically a Lambda function so that each time they upload a file into a bucket, they run a job on it to parse it and do something with it as a Spark job. And that's like really cool, right? That's exactly what we want with serverless computing. It's awesome. You put in your file and immediately like some work happens downstream. It's great. But then they also put in like 1 million files into this bucket at the same time. So now there were these kind of millions of API calls that were queuing jobs, and we absorbed all the jobs, and we were happily, trying to launch them on this person's cluster. So that's what was going on in there. So interestingly, though, in this particular cloud, there was a limit of 1,000 connections per VM between any VMs in different virtual networks, basically. So, so there was this limit on how many connections we could have between our servers and their cluster where we were running and monitoring all these jobs. And these were tiny jobs, so we were trying to launch a lot of them at the same time. And once you hit this limit, unlike a real network, this virtual network decided to just drop packets for any new connection that it sees, like any new pair of ports that you're connecting between. And it didn't even send back a reset packet to tell you your connection was shut down. It just dropped all the packets. So from the Linux kernel's perspective, these things were connections where it sent a SYN packet and it never heard back. So it was waiting a few minutes to hear back from that SYN packet before deciding that the connection has died. Okay, so that means that at least in here, some threads or some connections were were waiting to hear back from these SYN packets that they sent. So now, each of these connections where you're launching for a job, we assumed that would be pretty fast. So we had some state in memory, like for example, the details of what to execute in the job and so on, that we thought we'd keep in memory for a very short time because we're just going to send it to them once we connect and then, and then like delete that stuff. But now because these connections were hanging for like, minutes or like tens of minutes each, we were starting to accumulate a lot of this stuff in memory. And this caused memory pressure and garbage collection in this job service. It wasn't out of memory, but things were just getting slower and slower. And because of that, some of the health checks we had to existing jobs where we actually had an active connection, we were able to send packets back and forth, timed out. So we said, we tried to contact this job and we couldn't hear back for like 5 minutes, even though actually we were just doing garbage collection for 5 minutes. And then when this service woke up again, it said, oops, that thing timed out, let me abort it. And of course, that packet got through to the existing cluster and aborted it. So I think it's an interesting example of user isolation, resources and some of the issues that can happen here. Because, if you think about it, it does have to do with many users being together, but the resources that got exhausted were these like pretty weird resources. First of all, the number of connections per VM, something we hadn't really run into before, but that happened in this one weird case out of thousands of customers. This one weird group decided to do this thing. And so that was kind of a strange resource. And then there was also this, memory pressure where like we didn't crash. Actually, we had everything we need to keep existing jobs running and monitor them. But because of this GC pressure in the JVM here, we decided that a few of them timed out. And when you're designing a system, it's not as simple as having rate limiting and things like that to handle all of these kinds of issues. Cool. So some questions. What's the average heap size on the job service and on cluster nodes? What's the default GC? I don't know exactly, but I think the heap size on this was definitely like in the tens of gigabytes. And we chose one of the GCs that minimizes latency. But when you get large objects that are sitting in there for a long time, you'll still have, even these GCs will slow down. So eventually, the other thing that could have happened is that this thing would crash, which I guess would have been a better outcome. But on the way there, most things do slow down for a while. We don't have anything to shut you down if there's a lot of GC or anything like that. There's also a question about priority customers. Can you Do you like isolate premium customers? Do you give them SLAs? You can do that to some extent, and we actually have some of that. We have some ways that you can deploy just by yourself, but there are also disadvantages because if you isolate all of them, now you have to manage, like hundreds of copies of the control plane, and it's actually more likely that something goes wrong in one of them, and it's harder to catch with monitoring. So in many cases, we think it's better to have a single, like highly replicated, highly available control plane as opposed to something per customer. But of course, you do have a long tail, and some customers are placing large loads. So if you can do something special, for some of them, it makes sense. Yeah. Would the resource limits be solved by having a separate job scheduler per tenant account? It definitely would. It's just there are so many tenants. And as I said, managing like thousands of copies of the control plane is not easy either. But it's an interesting question, right? Maybe if someone can make that easy, it would be could be great to do stuff that way. We actually have other solutions to this that I'll talk about that are more about reducing the blast radius of failures like this, even when you have a single instance of the service. And I'll talk about how that helps, but that kind of helps you have the management, the ease of management of a single instance of the service without these like weird things bringing everything down. But there are other ways to do this too. Yeah. Okay, cool. So that's just an example of these kind of issues. There were also some things that happened, but were very rare. So for example, across like, 6 or 7 years of operating the service, we only had one time when a cloud provider said, we have to restart all your VMs, which was when Amazon had this Zen patch. I think now they can do it without shutting down VMs. They can just upgrade the hypervisor. We had one instance where someone had a security scan software that told them you've got malware on these VMs that are running Databricks. And then they thought, shoot, is there like a problem with Databricks? Did it get malware to run on my VMs? Turns out it was a false alert for them. But that's a pretty scary thing to have to debug if you think maybe someone hacked your customer through your service. That's not good. We had one big S3 outage that created these big enough issues to shut down jobs. And we had two kernel bugs that were actually very related to the kind of issues before. They both resulted in hung connections, and then they broke a bunch of assumptions, or like, for example, we could check if a node is up by talking to it on one TCP connection, and then we sent it stuff to do on a different connection, and the second one broke, and then we were confused about why it never did the stuff that we asked it to do, even though it seemed to be alive. So these are the ones that actually cause problems for us. Okay. So basically, the takeaway is that, especially when you've got something with an API and something that runs programs, and when those programs are trying to do large-scale workloads, your load is going to vary on a lot of interesting dimensions. And especially if you're going to rely on other services, there are more things that can break, including with internal and external services. So it's really important to think about how these will happen, how you're going to react to like something underneath you, not like hitting its SLA limit and so on. Okay. So this leads me to the second part, which is testing for scalability and stability. Now that we've seen some of these issues, how can we prevent them? There are obviously a lot of other things you can do to prevent as well, such as monitoring, but certainly it's nice to be able to test for them. So the way we've thought about these and our experience with these is that when you test for scalability and stability, it's actually quite different from just testing for software correctness. So just correctness is usually a Boolean property. You wrote a function, if you give it a certain input, does it give the right output or not? So that's what it means. On the other hand, these issues, scalability and stability, are a matter of degree. Every system with limited resources is going to run out of resources at some point. And the question, there's really like kind of two questions. What is the point where it runs out of stuff? what is that level of load, and then what is the failure behavior. There's graceful behavior, like, you know, like dropping some of the new requests or rate limiting people or stuff like that. And then there's ungraceful behavior, like, you know, bringing down the jobs that were already running on the platform or crashing everyone. And so when you're testing and monitoring and, you know, doing, you know, upgrades for a system that needs to worry about scalability and stability, these are the two things that you want to measure. So it helps to explicitly measure these two. Okay. So just some examples, you know, to give you another example of scalability problems. This is just for our basic, like this is our very first version of our product, which was just interactive notebooks that ran, you know, that connected to an instance of Spark and then ran some code on workers. Even in this example, there were a lot of different dimensions of the workload and of the system that could cause things to fail. So for example, you know, one of the first things people try to do is visualize large results, like large query results in their data. And if you're not careful with this, the large results could crash Spark itself. They could crash this driver app that feeds the results back to us. They could crash this service that's serving the web application. We even had things that passed through all this, but then crashed the user's browser. And so, you know, these were examples of some you know, scaling issues in each component. Same thing if you have you know, a file which has a large record or millions of columns in it, you know, large numbers of tasks in your Spark job, you're trying to display them in the UI and it can't display them. Any kind of code that freezes a worker. So actually in the first version of Databricks, we kept getting, you know, like every day as we added users, we kept getting these kind of issues. And we also, you know, once we fixed an issue, it would come back a few weeks later. This was before we built our scale test infrastructure for these kind of issues. So it seemed very daunting at the time to even get this basic thing to run really well as people were throwing more and more weird stuff on it. And then to make things worse, all of these are happening on shared clusters and of course the shared instance of the service. So these can also affect other users. Okay, so how did we handle this? So we actually designed this stress test infrastructure that's based around those two questions I mentioned at the beginning. This is something I was involved in designing actually back in 2014. So it was pretty fun to work on. And it's actually very simple, but very effective. So there's kind of 4 steps. So first of all, you identify the dimensions that you want the system to scale in. For example, number of users, number of output rows in your query, size of each row, or for things like talking to the cloud provider to ask it to set up VMs, the latency of that service, right? What if it goes from taking 30 seconds to taking 30 minutes? So you just identify all these dimensions. You can list them out. You can even add more later as you go along and discover things. So it's pretty easy for a team to just list out all the things where the, you know, where the workload might go. Then in our framework, we just go load in each dimension independently until a failure occurs. We would create a simple workload that you can parameterize and then just take one dimension at a time and increase the load, you know, by a factor of 10 each time. So try like, you know, 1 user, 10 users, 100 users, or like 1 column in your table, 10 columns, 100 columns, and so on. So just go it exponentially. And we found that 1 dimension at a time actually was sufficient to catch pretty much all the issues. Because if you exhaust a resource, it's very likely that you can exhaust it with just 1 dimension. So we didn't have to worry so much about the combinatorial explosion of how do you check across like, you know, 2 or 3 dimensions at once. That was an interesting insight we had from this work. And then once you do that, eventually the thing's going to tip over in most cases. So you record the failure type and then the impact on the system. So was there an error message? Did it just hang and time out? Did you get the wrong results? That's really bad. Did other clients get affected? Like if someone else was running a query on that cluster, did their thing break or could it still go through? And also, did the system auto-recover and how fast? Ideally, it would auto-recover and it would just tell you, you know, something went wrong, but, you know, here's, we're back in business and you can continue running stuff. And then we would just compare this over time and on changes. So this is the kind of infrastructure we hold out. And within like just within months of rolling this out, we were able to go from a state where like a new thing was failing, every week, and each change, caused regressions, to a state where like all these things remain stable, even though the number of users was continuing to go very quickly. So really made a difference just to run this and just push the system in each dimension and record these behaviors. If you want to see an example output, this is like a really old example where we were tracking these results in a Google spreadsheet, basically. And this is comparing 2 runs of a test, like it's literally copy and pasting some TSV files into there. So you can see there are these different test suites, and they each have tests. Like, for example, what if I have a big broadcast variable in Spark? What if I try to cache lots of objects in memory and they're large? What if they're really tiny, so that places GC pressure? What if I try to display larger rows? Like all these different things that we thought could create problems. And for each of them, we track the max value that the thing scaled to. So, we were able to broadcast up to whatever this is, like 1 billion bytes or whatever it is. And then we track the state, what happened to the system. So failed here is actually good. It means that it gave you an error message and said, I can't do that. And, nothing else got broken. That's awesome. Timed out is kind of bad because it just hung. We would prefer to avoid that. Succeeded is in the rare cases where it actually can handle that, because this cache, for example, will just not cache stuff once you fill up the memory. So that's fine. And there were a few other states as well. And then these flags here are other things that happen. Like, for example, the CB means that the whole cluster was broken and now no one can run commands on it. So that's something you want to avoid. Whereas other things like this SB is just that your shell, like your session, your notebook session got broken, but other notebooks are working fine. So that's okay. And then this is like the current value, this is the old value. And then you can see, some things improved, some things got worse between these two tests. So you can quickly highlight, okay, this thing is scaling to 1 step less, this thing actually got better, and so on. So very simple framework, but again, the really cool thing is how it went from kind of this game of whack-a-mole with like weird things that would break every week to suddenly everything's kind of working okay. So pretty cool outcome. Of what happened there. And the other thing I'll mention about this is, this is an example of an integration test that actually ran everything, but we also have, in many cases, we're able to reproduce these things as unit tests, so it's even faster to run them. This was actually a little bit too heavyweight, so we moved a lot of stuff into unit tests over time for these kind of issues. Cool. So hopefully that gives you an interesting example of how we do that. I'll also briefly talk about developing control planes as we roll out these new services, and a little bit about evolving big data systems. Okay, so developing control planes. So of course, I think everyone knows this. We've got lots of interacting, independently updated services. So how do we actually make these easy to build? So like many other companies, we have a team that builds a service framework and that everyone else can build on, and that can handle a lot of these issues. So our service stack handles deploying the same system into multiple clouds, such as AWS and Azure, and also into potentially special environments like customers who have restricted internet access to their VPC and stuff like that. So we want to abstract that away from our engineers. It handles storage, databases, schema updates, security tokens and roles, and managing credentials. So these things have the minimal access to other services in the systems. Monitoring, routing, and feature flagging. And we use a bunch of things. We use Scala very heavily. We actually use Bazel as our build system for that. And I think we've contributed a bunch of things to make Bazel work better with Scala. And we also use Envoy, Prometheus, JSON, and of course we use Databricks itself to monitor how the product is doing in many cases, and actually to implement some of our features where we give people analytics on their workload. What are some of the best practices we learned? So these are just things that worked for us. So in terms of state, we don't have that much state really, given the size of the workload. So we actually use MySQL basically for all the state, and we have per customer sharding, and it's usually pretty good. So that's kept things really simple. So every new service, we begin by designing the schema for what it's going to store, and that actually works pretty well for that. A more interesting thing is isolating components that scale differently. So I'll give an example for that, but in that jobs outage that I had, part of the issue was that we had this one service that was meant to both launch new jobs and do monitoring. And then when there was an issue with someone launching jobs, it messed up the part of the system that was doing monitoring, and that caused things to crash. So one of the lessons there is to isolate those and maybe let them scale independently, or at least like reduce the blast radius. If something's going wrong with launching jobs, don't mess up the thing that monitors existing jobs, which are happily chugging away on the data. Manage changes through feature flags. We tried a lot of ways. Everything you put out, you have to be able to turn it off and hold it back once it comes out. It doesn't matter how trivial it is. And so we use feature flags for everything there. And any other way that we tried had problems. Watching key metrics. So this is a pretty interesting one. A lot of people, when they talk about metrics, they think about very custom metrics like number of VMs launched per second, or like whatever, like commands sent to the cluster or stuff like that. But actually most outages, when something was crashing due to load, we could have detected that from these very basic system metrics, which are basically CPU load, memory load, database CPU load, and thread pool exhaustion. So these will usually catch most things. And in fact, actually, if you just watch these in like less, in like smaller regions, basically with fewer customers, you can often catch a lot of regressions in advance and not run into them when you deploy to the biggest region. So that was an interesting learning that, you don't have to get every team to like log, hundreds of metrics to get progress here. You can get pretty far with just these. And then the other one is test pyramids. So have most of the stuff in unit test, including things to do with scale testing. Turns out a lot of them can become a unit test, because if you don't do that, you just slow down the dev cycle because you have to run integration tests every time. So these are some of the things we ran into, and they helped improve the system quite a bit. Just to give an example of this second point with isolating components, this is similar to the job service. This is a system called the cluster manager, which actually launches and monitors the clusters that we're going to execute Spark on in each account. So this started out as a monolithic service where it served API calls like, please launch a cluster for me. And it talks to the cloud provider and it asks it to set up VMs. And then it also talked to the VMs to see what they're doing. So this had similar outages to what I mentioned with the jobs one, where, for example, when this thing slows down, or if there's an issue in the network talking to these, this whole thing, the whole service would run into issues, memory pressure, whatever, like thread pool exhaustion, all kinds of issues as the load increases. And so the idea here was to separate it into a master that handles the really important kind of stateful stuff about, which clusters am I supposed to be running and how am I billing people? Are we accounting for how long they executed and all that stuff? And this thing gets relatively few requests or operations per second. And then we have these delegates that are basically stateless workers that do the VM launch, setup, and monitoring, and they talk to this. And now, if one of these is facing problems, most of your clusters keep working, and basically the blast radius of that thing going wrong is quite a bit smaller. So this is an example of this second point, and it took a while to migrate it, but it's it definitely improved reliability quite a bit. Okay, let me answer a couple of questions about this. How do you guard against the service framework or API gateway becoming a new age monolith? I think there is a risk of that. So far, we haven't run into it, and it might just be because, we're pretty small overall. So we don't have a team there that's just like, that has nothing to do and is trying to add lots of things into the framework. They actually always have like pretty high priority things that they're doing, usually with one of their users. So it's, So basically, we don't see a lot of like extra stuff going in there that they won't maintain. And then the individual service teams are, we design our organization so that they kind of own their service end to end. They don't have like separate front end and back end, for example. So they're pretty focused on like anything they do should actually help their users. And they'll often kind of take matters into their own hands if something's not available in the service framework. They'll build it themselves, and then later they'll talk to that team about how can we share this across the company. So it's been okay. There's definitely a move, like as we move, we used to have some services, like for example, the thing that serves the web application that were a bit of a monolith, and we've been factoring those out, but that's usually been the biggest problem. Another question, have you considered something like shuffle sharding for workload isolation? I think this is about the Spark data plane, like how it does shuffles, if I understand correctly. And in there, the issues in there aren't as bad actually as the ones across tenants, but there are definitely users sharing a Spark cluster, and we have tried to isolate some aspects of that. Okay, oh, it looks like there's a library to do this. Okay, I'll take a look at that. I don't think I've seen that before, but it does sound, yeah, it should be pretty interesting to look at. I don't know if I can easily see what this is without messing up. Yeah, I'll look at it after the talk. Cool. Thanks for the pointer to that, though. Okay, great. Cool. So next. All right, so final thing I wanted to just talk about briefly is how do you evolve big data systems themselves to run in the cloud environment? So as I said, this environment's like pretty interesting because you have this massive scale and elasticity, but a lot of the big data systems, including Spark really, were primarily designed for an on-premise setup. So I think there's quite a bit you can do to really make them embrace this environment. And that's some of the stuff that we're working on. So if you look at the current, big data stack, it was really designed for these on-prem data centers where you have a team that sets up the data center, maybe sets up lots of other things like Zookeeper and MySQL, and then you get to run against that. But in the cloud, you want to get to somewhere where anyone can provision them. They don't have to set up like 3 or 4 auxiliary services and so on, and where these things are actually elastic. So I'll just give a couple of examples of things we've done. Delta Lake, which is an open source way to manage tables and have transactions on data lake storage. And then some of the things we're doing with running Apache Spark in a more serverless and kind of cloud native fashion. So Delta Lake, so motivation here is, we saw tons of users. As soon as you're using the cloud, you want to use the object stores like S3 and Azure Blob Storage and so on, because they're just kind of the lowest cost and most highly available systems for that kind of storage out there. They also have massive parallel IO bandwidth. So if you are going to store a large amount of data, it makes a lot of sense to just put it in cloud storage instead of standing up, let's say, a separate data warehouse or something like that, and having to manage that. And things like Hadoop and Spark could work against them, but not very well. And to get really good behavior on these, like for example, to get transactions or to be able to go back in time and edit your data and your table while jobs are running against it and so on, you would have to use something like Hive Acid. And that was designed for this on-premise world where you're also running a database and Zookeeper and stuff like that. So that was a problem for getting this to work well in the cloud. So these on-premise things, because they're smaller scale, they have stronger consistency, and they also, they assume you have a team to manage them. So the question was, how can we fully leverage these cloud object stores and give you very easy to manage storage systems without asking you to be an expert in running these things, and without having to run all these things ourselves, which can introduce more failures into the systems. So just a very simple example, let's imagine you're trying to write some output into a table or into a data set using Spark. Let's say you're doing this with HDFS. So one of the problems is, you're running a distributed job here. So as you're running this job, different tasks are going to write different files for your output. And some of the tasks might fail. Some of them might be slow. So you launch a backup task that's also going to try to write an output. For your own kind of sanity, as you have other applications consuming this, you really want all the output to appear atomically when the job is done and you're sure that everything has succeeded. You don't want to see partial output as the job is going and then have clients start to read some of that and then have it all go away because this job crashed. Okay, so how do you do that with Spark on HDFS? It's actually pretty easy. Basically, your job creates a temp directory. It writes all the partitions in it. And then HDFS is strongly consistent and has this atomic rename operation where you can rename this directory to the final path. So clients that are looking at this final path will only see it when you're actually done writing it. So kind of nice, very simple. You can also use this to append to a table atomically and stuff like that. Now think about doing this on S3. So the naive way to do it is you launch your job and you tell it to write, each task is going to write a different blob in S3. But the problem is that S3 is eventually consistent and it doesn't have atomic renames. The key, it's a key value store. So if you want to change the key of a particular object, you basically have to rewrite it and copy it somewhere else. And that happens one by one. There's no operation that lets you act on multiple objects at once because it's like, a globally scalable, like geo-distributed key value store. So you could try just having them write to these. There's no cheap rename. And maybe you could try a hack, like, for example, you tell clients, don't ignore everything in here unless they see a file that says that it's done. And then maybe that's going to tell them that, okay, now it's safe to read all the stuff in this directory. But even that approach causes problems. For example, if one of the tasks fails and it hasn't written this, you might, basically you need to get another task to write to the same object. And if in fact it didn't fail, it's actually just in the background trying to write it, then they'll clash about who writes it. There's also a problem with eventual consistency. For example, someone might see the done object, but they might not see one of these, and then they'll think there are only 3 files in the directory, and there were actually 4. So it becomes pretty messy to manage. And real operations are even harder. Like if you go back and you try to insert data into multiple partitions of a Hive table atomically, that's like writing into multiple directories at the same time. Okay, so what did we do about this? So we wanted a super simple, easy to operate approach. And our key idea was to rely only on the key value store and to basically use it to implement the transaction log. So we're going to track basically a big list that says which objects are part of a table at a given time, like which file names, right? Like part 1, part 2, and part 4 or whatever. And then we're going to store this in the Cloud Object Store itself as a write-ahead log. And we're actually going to compress the log periodically into Parquet. So now it becomes very fast to search across your entire table too. You don't have to do these super slow list operations to list millions of objects. You can just query a Parquet file and quickly see, which files are in there that maybe match a specific column or whatever. So, and we figured out, because it's a write-ahead log, we figured out a way to do this atomically on both S3 and Azure so that we don't need to run Zookeeper or MySQL or anything else. So it's very, basically the only thing that has to be atomic is appending to the log, and everything else, we'll use the log as the source of truth to deal with the eventual consistency. So the way this works is simply, when you run your job, you just create these output objects with different random names. Doesn't matter what their name is because clients are going to ignore them until they're incorporated in the log. And then you pass it through this different commit API for each service that appends it into this Delta log. And there's a way to do this atomically on each of the popular cloud object stores. And then actually querying this turned out to be about 10 times faster even than querying the Hive meta store in a lot of cases. So we actually gained because now we can query the log in parallel just by reading this massive Parquet file in S3. It's actually a lot faster than querying Hive or MySQL or anything like that. So this is an example of a kind of a cloud native storage system. We take the key value store as a given. This thing is massively scalable. It's like more highly available than anything you could really try to run yourself and so on. And we figure out how to make it responsible for all the hard pieces so that we get a transactional storage system that's as highly available as the key value store itself. Just to give you a sense of the impact, before this, about half the support tickets you were seeing were about cloud storage issues, like my data set is corrupted because my job crashed, or the output is wrong because of eventual consistency or whatever. And once we rolled this out, all of these went away. So it's like, it's a pretty significant impact of just this one, like, conceptually simple idea of relying more on the object store to do the difficult storage things. And we've also used this to build quite a few other features. Once you have this log, you basically can build a data warehouse directly on these objects. So you can support things like upserts and deletion, caching, indexing, where you maintain an index transactionally with the data, and you update the index whenever you add data in a safe manner, audit logging and stuff like that. So you can read more about this on the Delta Lake website. And it means that for a lot of users, they're able to, they don't have to worry about how to stream data between different systems. They can just get this familiar interface of transactions, but using at the same low cost as the cloud object store. I'm going to skip some of this, but there are some really cool use cases. Just at the Spark AI Summit, for example, we had, one of the first large use cases of this is for network security and intrusion detection at Apple. So there are basically like hundreds of terabytes of logs from commands happening on all of Apple's servers, network connections, employees logging into VPN, all that kind of stuff. And they have a team of hundreds of people that write rules to analyze these logs and to detect and diagnose, potential security breaches, or go back in time and explore petabytes of data to see, like, if an attacker broke into Apple, what systems did they touch? So this is just one example use case of like where this can be used. Yeah, so that's one example. There's quite a bit to do on the execution and computation plane as well that we're gradually doing. Things like auto scaling of Spark clusters and storage volumes, or kind of a serverless user isolated experience for Spark clusters themselves. So these are some pretty tricky problems, but if you can provide this, it obviously makes it easier for people to use. Cool, and then that's pretty much what I wanted to cover. I want to make sure I have some time for questions too. The main takeaway here is I think if you look at it, business to business software, cloud is really here to stay, and it just enables better products because they're self-managing, but building them is pretty challenging. And we hope to give you some light on how we're doing it. And we think there's also opportunities to do new things here. So I'd love to see, if people have new lessons or new service frameworks or anything else that that makes it easier to build these. Cool. And yeah, I'm happy to answer a few questions.
Thanks, yeah, let's please ask questions now, guys, as usual. And let's see how it goes.
Cool, yeah, maybe I'll stop the screen share just so if people can see each other in the cool picture panel view. I see, yeah. Yeah, I see one question from Alexi was about Delta Engine. So yeah, so Delta Engine is an example of how we're trying to create a more kind of serverless high concurrency environment for big data computation. So it's a new project. We just launched it at Spark AI Summit. It's basically a native execution engine for Spark SQL that can run Spark SQL and data frame workloads. And we're rolling it out. It's currently in private beta with users, but it bypasses some of the challenges with doing this in the JVM, with isolating users and also with getting really high performance on modern CPUs. So we'll see how that goes, but that's like one thing we've done as we see these high concurrency workloads. We think that underneath the Spark SQL API, you can implement this different engine design that can do them better.
Cool, thank you.
Yeah. Cool. Other
other questions?
I also see, does client implementation language play a role in implementing a large-scale system? So we found working on the JVM was awesome because there are so many development and debugging tools for the JVM ecosystem, and of course we use Scala for that. So I do think like writing services in Python or Ruby would be quite a bit harder, and you'd find fewer people who know how to operate those and who know how to squeeze out performance. And you know, I think there are definitely people who have had success with Go as well, but we just had this JVM background, and it's such a mature ecosystem that, you know, it just kind of made sense to use it.
Yeah, I have a question. I don't know, should I type
Yeah.
it? So when you use Scala, do you use anything like Zio, Scala Z, CAT, or something, some kind of like FP library? And if not, why?
We haven't been using those. We do have some custom libraries that we've built for specific things that we have to deal with, like accessing the database or handling feature flags, or even usage logging metrics. Like you can, for example, for feature flags, it's easy to create a context where, you know, you check which flags are active and do something in it. I think really we don't have that much to do that involves like heavy duty processing of collections. So things like Scala Z were maybe not as useful for that. But you know, we'll take a look as these things come up. You know, we might use them. Yeah, I'm trying to think. So Lee Howie works on our like developer tools and infrastructure team, and he's built a few things there using like interesting features of Scala. But I think like some of the most, you know, impactful ones were things like JSONet and configuration tools and stuff like that. At least so far, these were the biggest pain points. Yeah. Let's see. Okay, comments on ML workloads and streaming workloads. So yeah, for ML workloads, we do see people doing checkpointing, rollback, and distributed deep learning. We have quite a bit of usage of TensorFlow and PyTorch and scikit-learn actually on our product. And we actually have like these integrations in the UI and in the APIs for those. So I would say I don't think it's like that different in some ways from data engineering, in the sense that if you have a production application, you want it to keep working without bothering you. So things like fault tolerance, like can you recover from a failed node, and can you load from a checkpoint, and so on, are equally important in both of them. The most unique thing there is, I think, is deciding when to use GPUs and figuring out how to use them efficiently. So there's some work that we've done in Apache Spark and also in our platform to make sure that it's easy to launch GPUs and stream data into them from, you know, from data sources in Spark. Streaming in real time. And Apache Beam. So you can definitely run Apache Beam because it just compiles down to Spark. We have a lot of streaming jobs. We also have people who use streaming with this. Basically, they trigger the job to only run for a few hours each night, but they rely on the streaming engine to maintain state. So we have this like run now mode for Spark structured streaming that allows you to just run one batch at a time. So I think when I last looked at it, we had something like 100,000 concurrent streaming jobs on the platform. Many of them are small, some of them are very large. And the main advantage of this is that you don't have to do the bookkeeping manually of like, last time I ran my job, which data did I load versus not? And how do I need to upload downstream stuff? Because the streaming engine does that for you. The real time is less, in some cases, it's less important than this reliability aspect of like, how can I launch it once and then not have it page me for like months because I have other stuff to do with my time. So that's the main reason why people are excited. But of course, some of them are also doing pretty real-time things where they want to update something within seconds of a user doing stuff. Cool, let's see what else there is. Are we planning to use fibers? Haven't looked into that too much yet. It might make sense. It's just when you think about resource contention, as I said, there are so many other things that can be contended for, such as your database, your memory, all these things. So I think it's, instead of like focusing on just one mechanism at a time, like let's say to use threads more efficiently, I think it's even better to look at an architecture where, you know, something going wrong doesn't mess up everything else. What else is going on? Let's see. Comcast use MLflow plus kubeflow. If you're using MLflow, do you need kubeflow? So these, yeah, this is a pretty specific ML question. They do different things. So kubeflow is about how to stand up an ML stack easily on Kubernetes, which is useful if you're running that. But that's the main focus. Whereas MLflow is more about, you know, regardless of where you're running on, how do you have kind of this centralized hub to manage ML development? That's another interesting thing with ML. I could have said is that the software development and maintenance life cycle is pretty different. So we're trying to figure out what to do there. Cool.
Question by Parat. I don't know if he asked it yet. He asked whether client implementation language plays a role in developing large-scale systems. So I guess BNSF Scala, I wonder if you see differences in systems where clients actually are written in Scala versus clients written in Python or something.
Yeah, that's what I was saying. Most of our services are written in Scala, and that includes like how they talk to other things. And we like the JVM and Scala, both of them for different reasons. But it's just a big ecosystem with really good monitoring and debugging tools. So it's like awesome to have that. In terms of the end clients, we don't see as many issue with those really, because the place where we're using it, it's all in the JVM. So I can't really say about that. We do have a lot of users using Python as well, but these are more like the workloads that run in the data plane. They're not doing, you know, huge amounts of requests per second through these APIs. Yeah, and we use gRPC for to actually you know, package APIs and stuff. So you can easily create clients in other languages.
All right, and as long as it's allowed to ask questions verbally.
Yeah.
First of all, thanks a lot for this presentation. Thanks, Matej, for the delivery, and Alexei for arranging it. It was really insightful. So my question is mostly related to the foundation you selected for Delta Lake project. Spark was like, the place of Spark is Apache Software Foundation. And if it's possible, could you share your thoughts why you decided to find a new home for your next project?
It's just, so it's not a specific reason. I think they're both great foundations, and they're, you know, they have like really interesting projects, and they have, you know, like very solid communities behind them. So I think with Delta Lake and MLflow, which are in Linux Foundation, we also wanted to be close to the to a lot of the open source deep learning and cloud computing software. So Kubernetes is there, Onyx is there, Horavad, Petastorm, like some of these deep learning softwares are in Linux Foundation. So we thought that, you know, it would encourage more integration with those, but it's not like a huge difference either way. Like we, you know, and there are other things, like we also contribute, for example, to other Apache projects, such as Apache Parquet, and you know, we'll keep working with that. So and of course we contribute a lot to Apache Spark. We continue to do that. Yeah. So and you know, we also, like, we hadn't really worked as much with Linux Foundation before, so we also wanted to be more visible there, so that more of those folks interact with us, and you know, we make sure that these things integrate well with Spark as well. So instead of a completely separate stack happening over there.
That makes sense. Thanks a lot.
Cool. Yeah, I guess the other thing I should mention in the talk is we are, if you're interested in these problems, just like you know, shameless speech, but we are hiring, especially senior engineers on these cloud platform teams. So definitely you can reach out to me or whoever if you are interested in some of these, and you know, we'd love to to talk with you. Yeah. Cool, other questions? I see one on where is Spark moving in terms of deep learning support and GPUs? Yeah, so we have in Spark 3.0, the scheduler is now aware of accelerators. So that means you can run libraries that want to acquire GPUs and do stuff with them. We don't have too much in Spark itself yet, but there are pretty good integrations with existing deep learning frameworks. So we're hoping that those are going to, those are going to kind of explore like what's the best way of using these together, and then maybe over time we'll add GPU support in some of the things in Spark itself. So that's kind of the way we've gone with that. Yeah, and we have a lot of use of Apache Arrow for streaming data in and out of the engine. It's used for Python and R, and it also makes it easy to stream stuff into the GPU actually. Streaming based on event time rather than processing time. Yeah, so structured streaming has support for that. That's like the newer streaming APIs based on SQL. So if you look for like structured streaming and event time, you should be able to find some examples. Basically, you can say which of your columns is the event time and do stuff with it. That was one of the key reasons that we developed structured streaming. I'm just Googling it to see if it's easy to find. Yeah, there is actually, it's in the programming guide, but yeah, maybe it's not super obvious from the website that, that's the thing to look at. The older API, the low-level Spark streaming one doesn't have that, yeah. Does Spark have inbuilt support for event sourcing? There are a lot of people using it with change data capture to do event sourcing, but there isn't like a specific API. People are just building it themselves on top of event streams.
Going back to the streaming event time, you mentioned that the SQL framework, is that only available in SQL? Can it be used for simply transforming from one stream to the other?
You can use it. You can use it to have custom transformations too, but it's based on data frames and the SQL data model underneath it. So you can combine SQL operations and non-SQL and other stuff. Yeah, let me send a link to that actually.
Yeah, that would be great. In our use case, there are more attributes than the Scala limitation of 22 fields. So I was looking.
Yeah, this would be a good fit for that because you can use it. You can have a table with many attributes, and then you can pull out just some columns into Scala objects if you want. Yeah, and it's the same as the data set and data frame API. So you can easily mix like custom logic with with SQL operators if you and when you use SQL operators, it's likely to be more efficient. But yeah.
Thank you.
Cool. Okay, maybe I can take a couple more questions. I know it's basically lunchtime for people in the Bay Area, at least.
Yes, and unless you guys have any other questions, I think we should thank Matei for the great talk. We'll publish this video on Functional TV, which is our usual YouTube channel. It will be linked from the meetup itself. And you guys are always welcome to comment and send questions. I just wanted to note that it's very interesting to me, Matei, what you presented is basically a reactive system as defined in the Reactive Manifesto, which is resilient, elastic, message-driven. So this is very interesting to me, kind of relaunching the Reactive Foundation, that we are kind of grappling with the question, how can we enable all developers to write this kind of applications? Right, so I think it's very instructive to learn from these lessons. And the question, I guess, for us is, can we package these findings into easier APIs for developers? Because developers should not be really thinking deep about scaling the backend, right? Like they should be just using it as magically scales. So this is really
Yeah. This is something we're looking at as well, like whether we can adopt something like this or more reactive sort of technologies. So it's definitely on there. It's just it's kind of hard to do these as the thing is growing and changing underneath.
Right.
But yeah, it's definitely, it's like one of the leading ways to handle these problems.
Yeah, we have, that's interesting. It's not yet official, but we have R2DBC, which is the reactive DBC driver from VMware, and multiple contributors, kind of MariaDB and Oracle and others, soon inducted into the reactive foundation. And I think the interesting question is, if you really go reactive, you have to go end to end, because if you just do a piece of reactive, you will have to handle legacy systems and will not see big payoff, right? So that's, I think, an interesting question if you can go reactive end to end, but obviously with streaming, which is just native feed for it, and now R2DBC for reactive, I think interesting question. We would like to see Delta Lake supporting a reactive approach. That would be really, really cool.
Yeah, that would be very good to try to do, yeah.
Thanks, guys. Thanks again for joining us. Thanks, Matei. And we'll see you guys at the next meetup. Thanks a lot.
Yep, take care.
Hey, everybody.